All right, welcome everybody to a Dowel design of timber buildings. I'm not the handsome man on this image here. I'm Ringo. I'll be the host of your webinar today, but it will be mostly done by Adam Jones, our founder and CEO. So very quickly, who are we? We're Spec Toolbox. It's great to meet you. Those of you who know us already, it's great to see you again. And those of you who we haven't met before, we really appreciate you joining and being a part of what we're doing. We have a team of around 55 software and structural engineers globally. We used to be called CLT Toolbox. We're now Spec Toolbox. Our goal is to make innovative products easy to specify. We're being used in Australia, New Zealand, Europe, UK, and North America right now, and have been slowly expanding all the modules as we grow a global team. So for today, the agenda, this is a deeply technical webinar. That's why you won't hear too much more from me, but we'll be talking about Dowel design theory. We'll be comparing the different codes available and doing a simple connection example, moment connection example, and then talking about upcoming Spec Toolbox updates and the next releases. So for housekeeping today, we would love it if you put questions into the chat. So you'll see down the bottom there's a live Q&A that you can use. So we'll make sure that that's enabled for you. I think, Adam, you'll be able to do that. I can't. You can also ask questions in the chat while we're going. At the end of the call, I will be coming in and facilitating the questions after Adam's presentation. So once this is over, you will be able to access the full webinar recordings in our community forum, and you'll also be able to see them all on YouTube. So if you have teammates that you think you would have loved to have seen this, you can always pass it on to them. We try to build a bank of webinars across all the different regions and different contexts. So if there are things that you want us to do presentations on in the future, we want to hear about it. We want to work to provide the best education possible and getting the most out of our software and mass timber in general. We wouldn't be here without our list of partners. Those of you who have known us for the last couple of years know that this has all been growing really quickly. We are so grateful to the supply chain for buying into what we're doing and seeing the vision of what we can create. And so for any of them that are here today, we just always want to say thank you to them as well. So with that, without further ado, I will hand you over to Adam, who will be doing the webinar presentation today. Thank you, Adam.
Thank you very much, Ringo, and good morning, everyone. And welcome to today's webinar. So we're going to be covering quite a technical topic today on Dowel design theory. So the team have done an incredible job at taking a lot of complexity and turning it into simplicity, essentially is what we're looking to try and do. So essentially at the high level, so Dowel type fasteners are dowels, so loaded perpendicular to the axes of the actual fastener. So there's actually 5 different types that have the dowel type action. So in today's webinar, we're going to be looking at dowels and bolts as well. And dowels having no withdrawal capacity, but bolts you can actually, with their head and the nuts, you can actually get some capacity and with the head pulled through there. So that'll be covered today. So in terms of the design codes we're going to be looking at relevant in the Australia, New Zealand areas, there's quite a few that we've actually built into the software. So we have AS1720 built in. That might be the most helpful from a compliance perspective, but as you'll see, it's not a very sophisticated design code. Moving on from that, you've got the New Zealand code, the new version, which was in 2022. It's not really new anymore, actually, when you think about it's 4 years old now. It is using some of the Johansson yield theory equations as well, but that's so it's more advanced and it is built for, say, local timbers. So in New Zealand, that's probably going to be your best bet. But then we've got the Euro codes as well. So we have the 2004 Eurocode 5 built in, but also the latest version of the Eurocode. So we have the actual published version of the European code built into the software as well, which is probably the cutting edge in all regions. So we're going to be looking at this from the perspective of all regions. So firstly, let's look at AS1720. So this is the most simplified approach, and essentially it's a combination of checking if it's parallel or perpendicular to grain loading, to function of the joint group of the timber. And with that, you can actually use Hannikin's formula as well to combine the angles of the two if there's an angle to the load. So for this, quite simply, checking the capacity of the crushing. So the The timber component itself, this will be governing if it's a thin or weaker timber member, and then the yielding capacity equation of the dowel or the bolt in this instance as well. So based on that check, you then apply the local K factors, number of bolts, and then you end up with your overall system capacity. So pretty straightforward stuff. New Zealand, and we'll be doing real worked examples pretty soon as well. So New Zealand, on the other hand, it's a bit more advanced. So it gives you options for single shear or double shear. And for multiple shear, it gives you a series of double shear connections with the compatibility of the failure modes satisfied as well. So it is a simplified method. It's got similarities to AS1720, but does take from Europe as well. So with this, it's a combination of, say, the yield strength of the fastener, the embedment strength of the timber members itself, and there's the thickness, diameter, number of shear planes. And then also the rope effect if it's a bolt, and if it's a smooth dowel, you won't have the rope effect contributing to the overall capacity. So bringing that together, you got the different connection or the yield limit equations. So here you've got, for example, failure in the member 1, which here at the thin steel plate, member 2, failure in both embedment in both timbers, and then the yield failure of the dowels and bolts itself. For double shear connections as well, there's 4 equations to actually work from, and yeah, all of these are automated and built into Spec Toolbox as well. So the other inclusion, similar to Europe, is the inclusion of the brittle failure mode. So you can see here, parallel to grain, you can have the row of dowel fasteners failing as well in a brittle failure mode, or you can have them failing as a group in parallel loading. Alternatively, you can get splitting behavior as a perpendicular to grain loading component as well. And then, of course, on top of that, you've got the edge distance formula, and this is also another fail-safe for splitting of the timber member. If it's obviously too close to the loaded edge, then you're going to have splitting. So there's different checks that you need to do here based on the diameter of the actual fasteners and the relative edge distance. Slightly different, whether it's a perpendicular member or a parallel to whether it's parallel to the load or perpendicular to the grain. All right, then moving into Eurocode. So again, the 2004 version versus the latest version in 2005. So in a similar sense, breaking down what the actual individual capacities that you need to check, and then it's combined into the Johansson yield theory. So you got the yield strength of the individual fastener, you got the embedment strength of the timber. So you've got the rho K, which is the characteristic density, and the diameter of the dowel or bolt. And this K-mat, there's a lot going on underneath the hood there. So you'll see that in Spec Toolbox as well. But it's basically a function of a few things, including that of what timber member you've chosen, whether it's glulam, LVL, sawn timber. Then the rope effect check as well for bolts, and then the thickness, diameter, and number of shear planes. So if you compare the two codes in 2004, you essentially, the first thing you do is you split it into a thin, there's different methods, whether it's a steel wood steel or a wood steel wood equation. So you can see here the different checks that is there. And then the 2025 version is a slightly different version, where you can see here you've got the failure modes here. So the failure mode of this is a double shear. So that's what I'll start on the single shear actually. So a single shear to steel to timber connection, you've got essentially 5 equations. But the first check in 2004 was to figure out if it's a thin plate or a thick plate. So a thin plate is the how the plate thickness relative to the diameter of the dowel fastener as well. But the latest version, it basically skips that, and based on the yield theory, you've got the different failure modes here. So embedment in timber 1, embedment in timber 2, embedment in both timbers, and then the yielding equations of the dowel fastener itself. And this is the slide I was on a second ago, where you've basically got double shear, how that's treated differently, whereas the old code, essentially it breaks it up whether it's steel wood steel or wood steel wood, whereas the new code, you've got these yield limit equations that doesn't matter if it's wood or steel. It's a similar equations at the end of the day. But where it gets quite interesting and intense potentially, and relatively complex, is where you've got, say, multiple steel plates, and then you've got extra shear planes. So you can see here, and this is sort of one of the methods we'll be looking at, where you got 2 steel plates. You've essentially got 4 shear planes. So you've got a wood, steel, wood connection. So if you think about wood, steel, wood connection, you've got them on the outer, and then both the outers, and then you've got a steel, wood, steel connection, which is inside here. So steel, wood, steel, but on both sides as well. So that's multiplied by 2 as well. So you end up with 4 shear planes. So if you think if you're a dowel or a bolt carrying capacity, it's carrying capacity at 4 different points essentially along its length with those 4 different shear planes, and that they all contribute to the capacity. So adding a steel plate in there, you get a lot of additional capacity for it as well, but with some limitations of that. So for simple bracing fasteners, you can actually treat it as an overall system. So these can work together as a system of the overall load, and you get this system capacity. So that's basically the force divided by the number of fasteners, and the total capacity is a single fastener capacity multiplied by the effective number of fasteners. And then with that, you get the utilization of the total applied system load divided by the total applied system capacity. When it goes to moment connections, which we'll be doing an example on, all fasteners, they have different load shares, because you could imagine each individual fastener actually going to have a different force relative to where it is compared to the centroid as well, based on the lever arm and the overall resistance it has. So to calculate the individual force in every dowel fastener, basically simple statics is used to calculate the force of each individual one. So you do a combination of shear force, or it might be tension or compression load, and then the moment as well. So you need to look at each individual force that's going on at the connection to calculate the overall capacity. So following that, you've got the force of each individual fastener. You've got the angle between the load and the grain direction for each fastener is going to be different. As it, like, you know, if you say just a pure moment, you can see here how the force distributes along against the moment to provide the resistance. And you're going to have different embedment strength value for each fastener. And you can shall consider both the load share and load resistance, and then you take the governing for the fastener. So in summary, the old code and the new code for Europe, there's 5 failure modes, whereas 6 in the new Euro code as well, and double shear planes are treated differently, fundamentally differently. And then there's a multiple shear plane, so a series of compatible double shear connections. All right, so with that said, we're now going to do our first worked example. So this is we've done post and beam buildings a lot in Spec Toolbox in our historical webinars, but in this instance, we're going to be taking, say, a lateral bracing system. So you can see here, you can easily, off Spec Toolbox platform, do any of your existing analysis engines that you might have to work out the overall force of the bracing system. And then following that, we can work out the individual forces of the bracing member. So as you can see here along the grid line, so you can see we've done a quick mock-up of a design on an analysis tool that we've used. And you can see the governing being essentially at the bottom floor here to work out the governing compression, the governing tension load in the member. And both of these can be checked with a simple connection of the dowels. So zooming in a little bit further, this is what we're going to design for our first example. So we've got a 68 kilonewton load in tension and a 175 kilonewton load in compression. So before we get into that, I'm just going to, for those who are new to us today, I'm going to quickly jump into the Spec Toolbox platform. If you haven't seen it before, we've got individual design automation of different calculators, from basic things, CLT floors, fire design, penetrations, diaphragms, shear walls, penetrations, rib decks, TCCs, hangers, screws, light frame studs, connection details, brackets. So you can see here, and I'll show you a bit on what's coming in terms of acoustics and things like that today. So yeah, there's a lot in here. And so you basically, one way to look at it is a design automation of the calculations. But the other thing is the product suppliers who are on the platform, essentially, because you can design their products easily. So historically be using PDFs, but obviously with our platform now, it's really straightforward to design their products and the calculations. So let's get up the webinar example. So you can open the calculators from the front page, like I showed you earlier. Right now, I've got a few of the calculations we're going to be going through today as part of today's webinar. All right, so this is the dowel and bolt design. So you'll be able to see in our most recent, just let it load, on our most recent examples, we've got better visualization. So you got 3D, or you can really quickly just see what you're designing and optimize. So the first iteration here, we've got 3x3 row of steel dowels, essentially, and then a steel plate, a single steel plate as well. The member here, we've got an ash mass lamb 38 140 by 270. So this is the first example, and I deliberately chose this section size to have it not working, essentially, because then there's different pathways we can go to optimize, as you can see here. So you can choose number of steel plates, which we'll get to soon. You've got the force, so if you wanted to do tension or compression, just add a minus and it'll change in compression. And with that, you'll have the actual scope of the calculations change as well based on whether it's tension or compression. But let's just go back to our tension load as well. You can see the forces update as we go. So 75 kilonewtons, but if we added a shear force in a moment, like we will in future examples, that will be added to this connection. So for design methods, this is where we've essentially got all the different codes built in. So we're going to start on the latest version of Eurocode, and then the design data that comes along with that. So, and with everything, you'll be actually have, everything's well referenced, so you'll be able to follow along with the code to easily input it, but also more information as well. So I believe some of these are being wired up a bit more, so you're going to see more information on all key factors as we keep going. So next is the steel plate data. We've actually built a steel plate design module in here. It's quite an advanced for the European version. We haven't done the Australian steel design code yet, but if you want to just quickly optimize it, maybe the steel in the Eurocode is actually a bit more fit for purpose as well for this scenario. So we do have steel plate inputs. So next is your fastener. So right now we've got steel dowels, but you can change the bolts if you wanted. You've got bolt types, you've got distribution. So if I go here, zoom in a little bit. Right now we're even, but if you went uneven, you can see here there's different patterns. So we essentially lose one of the dowels there because we've got a staggered pattern, but then you'll have better dimension. It might be preferred from a geometry's perspective anyway if you did it. Soon we're going to have circular as well, so that's obviously something that's missing. Then you've got the fastener position. So we've got different options here. So every time you can define, I might move this, hopefully you can't see that. You can define the edge distance criteria. So you can do it yourself, or right now we've got the minimum edge distance based on the edge distances out here, and then it maximizes the spacing internally. But if you wanted to do the minimum fastener spacing, it's going to basically do the minimum spacing in here, but then maximize that edge distance as well. So there are different options, or you can just define it yourself. So I'm going to start with a minimum edge distance requirement, and you'll probably see it does impact the calculations down here. So yeah, all of these calculations well referenced, and you'll see in the geometry checks, they might be important to understand at the same time as well. Then you got the loaded edge distance as well, so you can play with that based on whatever you might have. So it's moving in. All right, so we're going to now go to our summary. So with our calculations, so these are essentially for the one-page summary. So this is just the main data that you could pull from as a summary, but you can see the different checks. So the geometric checks of the timber member itself, the steel plates, the timber member and the fasteners, and then finally you've got the failure modes I briefly mentioned before. You can see here we're failing in full splitting strength, parallel to the grain in this instance. So we'll try and optimize in a second. And then you got the steel plate design as well. So, if you were to play with the steel plate design, you can change the thickness. And you can see here we made it thinner. So the steel plate geometric check is actually the governing factor here, more so than the capacity, as you might imagine, right? So let's just move it back to just because we're going to be focusing on the timber primarily in this webinar. So it goes bit by bit before we start optimizing. So from a geometric check, the first thing is the timber member itself. So depending on whatever code you choose, it could be the New Zealand code, that's going to be changed in reference to get the right geometric checks, and they're probably going to be quite similar. So you can see the requirements in the new Euro code, so 2025 version, clause 11.4.1. You can see here, so spacing along the grain, minimum 5D, so it should be well spaced out here. We're always trying to improve our UX basically of this as best we can. So you can see A1, well referenced, A2, spacing along the grain in the perpendicular direction is A2, the loaded edge distance, which is A3T in this instance, and so forth. So the loaded and then the unloaded edge distance as well, based on the unloaded side as well. So they're the edge distance criteria. We've also got edge distance criteria, the geometric checks for the steel plate. This is a function of the thickness as well as the end distance here. So, but again, everything's well referenced, and then the checks here based on Eurocode. So you can optimize the steel plate as well. The other thing we've got here is the steel plate. So, sorry, the stiffness. So the calculations of the stiffness based on Eurocode as well. If you wanted to use that, and maybe important if you're doing a portal frame or something like that to get the stiffness of the overall connection, but that's all calculated there as well. So next is the design parameters. So these are the parameters which are then used for the yielding resistance equations, as we can see here. Later, I'm going to show you the new UI UX we're working on as well, because it may be these green ticks we've had feedback look like they're utilization checks, but it's meant to be scope of the report. But anyway, I'll share that later. So design parameters, some of these are basically built for the moment connection, these images. So as well, so not all of these are relevant for every connection. We'll soon build in some smarts to hide the imagery based on if it's not a moment connection, but maybe I'll check on the moment connections later for that as well. So the most important one is as we go to here. So for the fastener result, so what is the actual load carried by each individual fastener? So I think we had about a 68 kilonewton load, but then you've got one shear plane, and then you've got 9 different dowels essentially here, but they're all highlighted in green because they are all the governing connection, because it's a simple connection. You'll see in the moment connection soon, if you added moment, it will highlight the governing equations. So we've built it ready for moment connections, even though it's a simple connection in this instance. And you can see what's the utilization here as well. So then you've got each shear plane. So the resultant force in each shear plane of each individual fastener is included here for vertical shear and also the horizontal shear as well. So all of this just lays out before we get into the yielding resistance. So for the yielding resistance, this is when we get into the meat of the equation. So for the design strength, you've got the embedment of the steel plate side, you've got the embedment of the timber member, you've got the beta value, which is the ratio of the two, and then you've got the fastener yield moment, as I mentioned before as well. Your calculations for the rope effect, because we're using dowels, this will be 0, but if you change to bolts, you'll get some capacity of the overall rope effect as well. All right, so we've got we've got in this instance, we've got only a wood steel wood connection. So when I show you a double steel plate, you'll see new complexities come in. So here we've got wood, steel, wood. So it's a pretty straightforward calculation here of the different failure modes, embedment of both members, and then actually the yielding of the dowel and bolt itself. And that's the individual checks as well. So the minimum here is the 9.39 kilonewtons in this instance. And then that's moved into the next set of equations. So here to get the actual the lateral resistance per shear plane of a single fastener, and then you multiply that by the effective number of fasteners in this instance. And these checks here brings us to our design resistance, which is 91 kilonewtons. And I think we had about a 68 kilonewton force. So utilization in this instance of 72%. So this isn't the thing that's governing in this instance, but we will soon see what is. So next we've got the brittle failure check. So as we mentioned, you've got the row of, so we're basically pulling out here in tension. So you've got the row shear, so the row of dowels in this instance pulling out. With that check, you got all the individual equations here. So these are all well referenced, and you can easily follow along the equations. But for this one, we're not governing at 10%. Next, you got block shear resistance. So you can see the equations here, what it's a function of. So it's the combination of the area of basically the area of the dowels and the bolts. So it's you'd expect the strength of the timber member to be a big part of the governing resistance here, but in any instance, we're at 20%. You've got plug shear resistance as well. As you can see, the failure modes here. And then finally, the net tension resistance as well. So, that's 21%. And then we've got splitting capacity parallel to grain, which is the final check. And then that's failing at 164%. So we're going to do some optimization in a second. And then you got the steel plate checks if you wanted. And then the timber cross member, this is going to be in the next day or so. We're going to do basically based on the code to check the timber with a reduced section as well. So the steel plate, all the strength checks here as well. So 7.7%. So we're not even close to governing. As you saw before, the geometry is where it potentially governs in that instance. All right, so we're failing in the brittle failure mode. So let's start optimizing the design. So let's imagine if we do two steel plates. So we've got new shear planes developed. So you're getting more bang. So let's just think about it in terms of cost. So you're going to get more bang for buck in terms of each dowel in this instance, but you're going to have another steel plate and you're going to actually have another cut inside the timber member. So it's all about trade-offs. What's the most cost effective? And I think that as a designer, is one of the ways you can make a really cost-effective design. So I've done two steel plates, and right now we've got it significantly reduced here. So now we're actually getting significant improvement when it comes to full splitting strength. And one of the reasons is, in terms of everything now. So because now we've got essentially additional shear planes. If you go in here, as I mentioned before, you've essentially got wood, steel, wood. You've got steel, wood, steel multiplied by 2 in terms of shear planes, and then you've got another wood, steel, wood. So in this instance, we've actually calculated things. So here you got steel, wood, steel. So that's essentially the failure modes here. So, you can imagine failure of both steel plates, which I'd expect a big capacity there. Yes, so 90 kilonewtons, the timber member itself in the middle and so forth. So that's for the steel, wood, steel component of the connections. And then you've also got the wood, steel, wood. So both outer planes as well. So these are all calculated individually. And then following that, because you've got 4 shear planes, as I mentioned, 2 in double shear, how do you combine them? So this is probably where the complexity comes in, and a powerful software like ours is just going to make life easy at the end of the day. So here's your different combinations of the different failure modes to work out the capacity. So you'd add them all together. In some instances, the code doesn't let you add some failure modes together, so it's not compatible because it's not realistic. And that way you don't get any help from that failure plane. So as I said, you've got 2 outer shear planes on the outers, and then you've got 2 inner shear planes. So you add them together. So it'll be 2 times the failure mode A plus failure mode A of the steel, wood, steel plus failure mode of the B gets you to 40.6 kilonewtons. So there's a lot of different checks, and then you do the minimum one. So in this instance, we got to 33.9 kilonewtons as the minimum failure mode here as well. And then that's calculated in a similar way. So with that, you get extra capacity there. That's for the yielding equations where you get help. But as we were failing before in brittle failure mode as well, we're spreading the load a little bit better, and we've now got it down to 45%. So that was one way of optimizing. Another way you can optimize is, let's go back to one steel plate, for example. So we'll be failing again. You could just add more rows and more fasteners per row. Now we've got that working again. So with that, you go from 9 to 16, so 7 more dowels. So maybe that's more cost effective. I'm not sure. Or you could obviously go back to 3. You can change the bolt type. M14. So there's different ways you can optimize. So probably these days you could use AI to find that out, or maybe we'll be integrating AI soon to help with some of those things. Obviously you can change the grade of the timber, which I'll probably say is more expensive, bit of overkill as well. But yeah, so if you wanted to, from there, just change codes and review it. So now we've got the current version of the Eurocode, and you'll be able to reference that. If you were interested to see where the updates were, or if you were to go to, for example, the NZS AS1720 code, now you've got the local capacity factors, local K factors, well referenced here. So, and now we're failing in different failure modes, and it's designed in a slightly different way. So, yeah, I'd recommend, depending on where you are. So obviously in New Zealand, you'd use the New Zealand code. In Australia, you may consider the Euro code as what's updated. But in any instance, it's all automated, and where there's gaps in code, like there is a lot of the case in Timber members, we sort of just try and make each one easy and then give you the power to check however you want it, basically. So that's our first connection, a simple one. I mentioned, so tension, let's just do quickly on compression. So minus 175, this will now change to a compression load. Now the scope's changed. So we've got a higher load, yield resistance. We don't have all the failure modes before because it's not in tension, which is great as well. But you can see here we're failing for the geometric checks. So let's just go minimum edge distance criteria. That's just a way of quickly getting your geometric checks right. So we've got algorithms to make it easy. And then again, if you go through all the calculations, let's just go 2 steel plates. We're still not working. Maybe we'll go 4x3. And now we're working, you know what I mean? So that's hopefully pretty straightforward. And then maybe you just make it uniform as well when you do the design. So that's how you do the compression member. Next, we're going to do a moment connection here. So we're going to do a single shear here, but then there'll be an induced moment on this member here. So similar bracing, not every time you design these as moment connections, to be honest, but you could imagine in industrial building, designing it in a similar way. So anytime you've got a moment connection, hopefully this will be done easy. So let's just go back to Spec Toolbox. So shear only. Really easy to duplicate our calculators. So you can just duplicate the same member, same dimensions if you want to just keep it uniform as well. Got another from our friends at Ash. In this instance, just inputting the shear force as well. Input the data. So I went through all that before. You can see here what are the different failure modes. So in terms of, because it's, where are we? So stiffness calculation, design parameters as well. So similar to before, fastener results, yielding resistance, and brittle failure mode. So as you can imagine now, we've got splitting, it's a lot of perpendicular to grain loading. So that's the splitting check in this instance as well. So that's, that's all built in. In this instance, we're failing from yielding on the first input. So again, you can do a quick optimization to quickly get your design up and running. Next is the moment part of the connection. So as we transfer the 78 kilonewtons, so that's going to be transferred in as a compression force. And then we're going to have a moment induced as well by the eccentricity of this part of the component as well, which is a 17 kilonewton meter loading. So let's go to this. And we'll spend a bit more time on the moment connection now. It's worth mentioning on a future update, we're going to allow Automate have multiple members to do all those smarts yourself. But in the meantime, you're just going to have to create individual calculators, and it's probably easier than any other way, to be honest. All right. So in this instance, we've got 78, so it was a 17 kilonewton meter plus a 78 kilonewton. So let's just go 17 kilonewton meters in the bending moment. Now you'll see a bending moment inputted. I think it's on the other side. Yep, so 17 kilonewtons plus that. I think that's not there. I think that's meant to be a compression load. So let's give us a moment. Input the forces. Yep, so 78 kilonewtons. Because it's 3D, you can see it's sometimes the text overrides each other, but I think you've got the point there. Latest version of the Eurocode, steel plate data as well. So all pretty similar in this instance. And you can see here where the different areas that were failing as well. So we're going to inspect it a little bit here. So geometric checks, you can see all everything referred to there. Stiffness of the connection and then design parameter. So remember I said it, well, for a moment, you're not designing individual, sorry, you are designing individual fasteners instead of like a system in this instance. So you can see here the theory behind it based on the dimensioning and how we end up getting a force on each individual fastener based on the induced moment here as well. So yeah, so for rectangular group of fasteners, so again, it's a combination of the angles and the different formula here as well. So with that said, there's a bit going on. So you get a resultant force for each individual shear plane as well for the fastener based on the bending moment as well. So this parameters is basically just setting you up for the calculations and just doing those extra checks, embedment strengths, the modification factors, your K90 factor if it's relevant as well. So you can refer back and forth here as we get into the design. So for the fastener results, we got to get these a bit more to scale, as you can imagine, but you can see here how the force is a bit more circular here and the individual fastener ID, which are the governing ones essentially. So you can see fastener 2 and fastener 6, 2 and 6 are the governing fasteners. These are the ones that are taken into the design in the next check as well. So depending on the load and the forces, these will change. Remember before everything was equal and it was governing, but now we've got a moment you to go fastener by fastener as well. Similar to before, resultant force per shear plane in whether it's vertical or horizontal, but also the resultant force as well. Next is the yielding resistance. So this is a bit similar to before in terms of how it works, because now we've basically used simple static theory to get the individual forces. And then from there, you actually do the checks again. So again, the different failure modes, so from wood, steel, wood connection as well. And then the different checks, so the effective number of fasteners, and then you get the overall capacity. So again, we're failing at 611% in that instance. And next you got the brittle failure modes checked in detail as well. So with that said, as with all of our checks, look at it in detail, not a black box. Being not a black box is great for us because I think these calculations need to be transparent. There's a lot going on, to be honest, and we find if there's anything a bit weird going on really quickly in that instance, and so can you. So we recommend you coming out. So let's just go 3 steel plates. We got a bit closer. I think 4 steel plates, we might start running into geometric check problems potentially. We're getting closer. We're getting closer. Let's go M12. M14, yeah. So you could sort of, let's go 4 and 4. So just for the sake of the webinar. So now we've got it working. So there's a bit more going on here. So you've got to resist this check. Looks like a lot of steel plates there. I might just make it 2. Just using a bit of judgment. Yeah, we've still got it working, which is great. So yeah, because not always, I believe, this is what Beza was telling me yesterday when she was, she built this alongside Terradros on our team, that no, it's not a linear, add more steel plate to get better capacity like we just saw then. So yeah, but at least you could just quickly optimize and check how it's going. So yeah, they're the checks for today's webinar. At the end, hit save with all of our calculations. We've got a summary report for 1 page, or you've got a detailed report. Just take a couple of seconds because there's a bit to print here. And then you'll have your calculation pack essentially that you can send to the certifier for review. We've also got a 1-page summary. So usually the way you do that is like you might do your detailed report for one of your connections, but then for So then you've got all your calculations built here essentially. So it just basically prints out everything you need. So we assume a certifier needs this detail sometimes as well, right, to know what's going on. So yeah, it's all there, well calculated, how it all works. If you do a summary report, I've never done a summary report, so we'll learn together. And these are usually harder as a serve error, so there's something we got to fix there for that. So there you go. All right. So yeah, so that's the Dowels and bolts. We'll take questions soon, but I thought it'd be good to just take you through some of the latest updates. There's a lot of stuff going on in the background, which we're really excited to share with you as well, and basically get you a first peek. I might start on our new UI UX, just for your curiosity. So I think, like you may have noticed in these calculations, it's probably headings. You know, we don't really have a good template at this stage as well. So, you know, look at the amount of fasteners now, the ID, right? So there's a lot more going on for a moment connection. So just a side note, yeah, I think it's pretty good, but it's essentially, this is where we're moving to from a design perspective. So we're going to have inputs up here, easily referenced. So you could basically do responsive as you're doing an input, the 3D here, and then all of the calculations built here in detail. So there'll be a new input plane here, which hopefully improves things a lot. So very quickly, you should be able to responsively change an input and know how it's checked. The other thing we'll have here is the ability to, this will be like an index as well. So when you click in and out here, it'll go to that specific calculation that's failing, right? So you can quickly go in, optimize, quickly jump back out, change your input. So that's where that's heading. Also now outputs are pretty messy now, but so the calculation flow will be much easier to follow as well. So these are good things to look forward to, our new templates here. So you're going to see them coming in the coming weeks. The other thing worth mentioning, so in terms of connection details, we're relaunching our details. So we're going to have a big improvement here. They're just going to perform much better as well. They'll be in the new design when they release as well. But yeah, we connected them to the individual screw design modules, and we made 3Ds. So for a spline joint, like very quickly, you can change the materials here, densities. So really quick to do the design, fastener data. Yeah, sometimes we don't always get enough credit, I think, for ETAs, but yeah, you have the ETAs built in of the individual fastener suppliers as well. And so yeah, really quickly doing your designs in this instance here, but with better 3D visualization. So yeah, half lap splines and butts, and then there'll be a lot more connection details soon released as well after that. The other thing is our fire design module. So similar thing where we've done a few different options, and this will lead into acoustics in a second. So I know everyone didn't sign up for to see this stuff, but if you're in the massive timber industry, hopefully this gets you pretty excited, some of this stuff. So traditionally you'd have to open a different floor calculator and a fire calculator. Now we've started the ability to basically combine the scopes together. So when you click here from a fire protection perspective, you got all the fire calcs in here, and you can add protection, add multiple layers, fiberboard, insulation, whatever it could be. And then with that, you're adding more protection as well. So again, really quick and easy to optimize the design as well. So, so you go, where do we want to go? Mineral wool. You got your joint types. Sometimes that is the governing behavior. Let's make this like 45 millimeters for mineral wool. Take a few seconds to load. So this is in alpha. So it's not, so everything I'm showing you now, it's in alpha, hasn't been released into the app yet. So it's final stage review as well. The other one, what was I up to there? Yeah, it's fire. The other one's the shear wall calculator. So this one also pretty cool. So again, late stage review. So a lot of this will be just, you'll see some updates in the coming weeks or month essentially. And all of these are going to be in all regions. So Australia, Europe, USA, and Canada. So again, here you've got a shear wall design. Let's just go what do we got? A wall member from Binder's panel. But yeah, the difference here, the upgrade here, we've actually now got the ability to add your angle bracket data and your hold down data. So we've integrated bracket supply chain here. You can, so yeah, angle bracket, you've got all their bracket families, patterns, sizes. So very quickly you could do a well integrated shear wall design. Yeah, with all your factors there as well. So yeah, pretty good, pretty advanced design. You can imagine how much QA we need to do before we push something like this live. So that's that. And obviously you got a 3D visualization. In the US, we've got multiple shear levels, multiple stories. So they do allow that a bit better in the code. We don't really have that built in for Australia yet. So obviously that's a dimension. So it's that. And the other one just worth mentioning is acoustics. So the way we're going to work, so remember you had structural and fire before, you'll have acoustics integrated with structural and fire, which will be great essentially. So we got our first acoustic supplier, woo, go B&C, they're awesome. But yeah, so you'll be able to, their build-ups and their layups with the specific tested systems. We've been having great guidance from acoustic support in this instance. But yeah, choose your layups. And then for your rating, so Australia, New Zealand, you'll have AAAC or NCC. So NCC is either fail or pass. The AAAC Air, I forget the Air something Acoustics Association Council or something. But yeah, that's all built in as checks as well. So with that, goes into detail of your spectrum. The spectrum analysis? We're using mass law-based analysis, so there's some good reason behind that, airborne, impact, and then your overall rating checks as well. So yeah, that's built in, also not far away. So there's a lot of cool stuff just about to drop. Yeah, and then hangers. So hangers is probably maybe the biggest, from my perspective, it could be the one that users might get the most excited about. So what I'm about to show you, it's in alpha. So again, late stage review, not in app. So please forgive me if I need more than 3 characters there. So please forgive me if there's a few things being worked on here because it's not in app. So this is, yeah, this will be very buggy at the moment as we work through the kinks. That's what I'm trying to say essentially. So give it a few moments. So yeah, so you've got beam to column or beam to beam. Let's go beam to beam. Connection, all the views. We're building in a 3D view. The idea is to get into a export to DXF. You got your different hanger types, design methods, geometry. So let's just say if we go to an ash, this might bug out. Let's just get like a really sick beam to column. What am I? Primary member. So this is the column. Sorry, this is the beam. Sorry, the other one, other way around. Sorry. Let's go. Let's just quickly go 290 by 290. It'll be an ash into an ash. Let's just size it up quickly. Yep, so that'd be like a beam to column connection. And then to connect the data, the cool thing is we're gonna, again, you can choose the connection that you're after. So Rotho, Eurotech, Pitzel, the first one's the Australia region, US, Canada, we've got different groups coming on. But yeah, easily do your design, loading data. Yeah, we're using it. This will take a few moments to upload. But yeah, if you looked at the Pitzel European Technical Approval, which is an ETA, it's quite a detailed calculation going on. So if we go calculated capacities, let's go heavy duty. Bit risky because this is late stage. So let's just go a bigger item, mounting options. So yeah, again, your different options. We go back here, you'll have the hanger imported perfectly here, getting some tolerances built in. So yeah, that's a bit going on. Capacity. So these are the checks based on the ETA of the individual screws. So again, supplier by supplier has got different ETAs, different data to calculate on. So yeah, this is also something to look forward to in the app and solves a big problem that's missing. All right, with that said, I'm going to try and find where the webinar is. So we'll stop there. I'll stop sharing my screen.
Hey, well done, man. I love those updates as well. So Thank you, Adam. We are up to the live Q&A now. We do have a question from me as well, so I wanted to open with the question from me. I was just curious about which modules the fire calculator is going to be connected to initially. Is it just the floor, or?
Yeah, good question. So I'll give you a quick demo of, say, the column calculator, because I think that's someone trying to call me. Get rid of that. Yeah, so the column. So I believe it's integrated here. So you'll soon see the fire ones retired, because they'll be integrated into the column. Just give us a few moments. So yeah, the beams and the columns essentially as well. But I just want to give you a quick demo of what the column looks like, because you can imagine, based on, if you got, like, think of that hanger connection I showed earlier. Yeah, you could have an unbalanced load, and what's, so like you can imagine here, right? So I'm just going to quickly just do connected beam loading. So depending on what face is exposed to the fire relative to where the beam connection is. So let's just imagine you got like a beam here connecting here, but then you've got the fire coming from this side, then it'll get less conservative as well. Whereas if it's a fire on the other side, it's more conservative. So there's a lot of complexities there from the fire perspective, which I'm excited to get. And then again, so all you do is like both sides exposed, both faces, and then you've got your fire design, add protection layers. So it's going to do all the calculations based on that. So yeah, fire for both.
Wow.
Ready to go.
And we had two questions from Anonymous. One with a thumbs up. We'll start there. Is there any way to export to Revit? Yeah, it's a pretty classic question. Yeah. So is there any way to export, say, like that Dowel design right now, or?
Yeah, not at this stage, but that's something we're actively working on now. It's to be more interoperable in that instance. I think I've been saying that for over 12 months now, but we really are. Like export functionality and import for CSV is obviously going to be important, and then and then getting it into the Revit environment as well. And a similar one is like, how do we integrate AI into the calculators is something we're working on. So because you may how before I was like scrolling, finding things yourself, and maybe you could just ask it, an AI to help find out, learn about all the information inside the calculator.
Yeah, we should probably do a future webinar just on that. I would imagine it's a pretty topical question that people have. And the last anonymous one that we have here is, is there a functionality for help designing in a seismic region with the Dowel calculator?
Yeah, that's a good question as well. So that comes up a bit. So yeah, we'll have Eurocode 8. We're going to make a big push for as well. And that's again, because it's the timber code of Europe, and Europe's the most advanced. So that's probably like the go-to we'll lean into. And there's, I don't know all the detail myself, but the team's onto it. They're like ductility classes of it. And then, because you don't want brittle failure, essentially.
Gotcha.
Yield equations.
Brilliant. Well, are there any other questions from anyone out there before we start to wrap up? No? Amazing. All right. Well, I'll just move to the last.
Thank you, everyone. Cheers.
The last couple of slides here, basically just the next webinar. So this will be done next month, May the 14th, 2026 for ANZ. And that's it. So again, just want to say thank you to everybody for their time today and attention, but thank you in particular to Adam for the effort that he put into this. And we hope that you have a great day. So thank you, everyone. Bye.
Thanks a lot.